Good morning, plant breeders, plant scientists, people working to improve genetic gain night and day. Hey, we really need you because the world population is increasing. Food security is always an issue. So it's just the way it is. So quickly, this is David Benson with Cornhusker Hybrids LLC in Lincoln, Nebraska, where our trademark is success starts with the seed. No better statement has ever been made in this business. Look, today we're going to talk about my favorite topic, genetic gain. And where it's going to be kind of a brainstorming, free-for-all, kind of let the chips fall where they may type discussion where I'm just going to kind of bring things up and try to make sense of how they're improving genetic gain. And so I just entitled this video, Genetic Gain. Are the new technologies increasing or improving genetic gain or not? When you talk about genetic gain, and just to keep people focused again, as you know, this is the classic genetic gain equation that I learned during my tenure as a plant breeding student with Walt Fair at Iowa State, Agronomy 521. And anyway, what it says is just that your selection intensity times your parental constant, which may or may not be a factor for you, but it could be an improving genetic gain, which selection method you choose. Kc sigma squared A, so your additive genetic variance, and then it's over the phenotypic standard deviation, which is the square root of the error variance divided by the reps and environments, the genotype by environment interaction variance divided by the number of environments, and then sigma squared G, which has A by D, D by D, every kind of genetic component of variance in it. Epistasis is somehow in there. All those things are there in that delta squared G. But that phenotypic standard deviation. And then, of course, everything revolves around years, right? The fewer years you can take to cycle your population, the greater your rate of genetic gain should be, and that's where doubled haploids have come in. But if you look at the genetic gain equation, where are the places you can improve it? I mean, years are about, I don't know if you can get them a lot less. I suppose some point in technology you will, but right now they're reduced about as much as you can when you take doubled haploids or however. Now I just want to stick this one out because this is the Borlaug equation, just for reference quick. And they cut through all the chase and they just have your selection intensity 10 times your accuracy of selection, which increases all the other variables that are in a phenotypic standard deviation by your additive genetic variance. And so it's just a result of selection intensity, accuracy of selection, which comes out and how much additive genetic variance you get over years. So where are we going to improve these things? We've got the selection intensity, you're not going to be able to do much because most people select pretty high, 5, 7, 10%, maybe some even 3. You can't select much more than that. Secondly, your years, you can only increase them so much, and they've taken a huge decrease when we went to DH. It did decrease some years, at least in maize. So anything you can do to decrease the time of a cycle is going to help you, but I'm not sure you can do a lot more of that. Accuracy of selection is where you got to work, right? So just keeping that in mind. Now, secondly, keep in mind, breeders, that your breeding program has to operate in a way. All it has to do is retain the better genotypes, superior genotypes for continued evaluation and selection. So what I mean by that, you don't want to be throwing all your best genotypes away the first year or two. Now, you will, and we have, because you'll never know it. But your idea is you want to kind of have an elastic phenotypic variance, if you want to think of it, that kind of goes across years and environments, and that phenotype's got to have a little elasticity to it. So when you get down to it, what do you got to do? You got to increase your genetic variance, right? You got to have that phenotype that you're seeing or you're taking data on. We've got to have as much of what we're seeing there. The more of that is genetics that we can control and understand, the better, right? And the more sigma squared A there is. And additive genetic variance is the raw material for selection. I mean, it's the genes that combine additively and independently of one another, and that's what you want. I mean, so when I look at the genetic gain equation and I think about what I see coming across LinkedIn quite often nowadays in other places, I think the sigma squared G is, we're into that genomics, the phenotypic standard deviation in that, and any time we're looking at phenotypes, we're into phenomics, and the G by E term is environomics, if you want to think it. So you could think of the equation, I think, that way if you want to. Now, everything, again, when you look at genomics, you want to increase, your understanding of the genetics and the ability to select the genetics. Also realizing that you got to have kind of an elastic phenotype. I mean, it can't be rigid. It's got to be able to respond to the environment, especially a changing environment. Phenomics, I mean, you're just improving the precision on your phenotype. What you see, whether that's through roots or leaf angles or carbon uptake or photosynthesis or any number of things, it's coming down to that phenotype. But again, that phenotype has got to translate over into improving the additive genetic variance. In environomics, I mean, heck, anything you can do to decrease the genotype by environment interaction or manage it or maintain it at some given level is better. I mean, why G by E doesn't really help you. I mean, it makes that term, anything down there that's bigger, makes your genetic gain smaller. So let's just take for a minute here, and I'm going to cut to the chase. I'm going to get to the end of this talk today. What about the new technologies that are out there? I mean, every time I go on LinkedIn or I go anywhere, I'm seeing robotics, I'm seeing UAVs, I'm seeing, AI constantly, everywhere. And so what is it, really cut to? I mean, so I kind of think of it as, well, we're looking at this phenotype, and now we're able to, is robotics helping us improve the phenotype? Well, certainly robotics, the main thing robotics does is it saves human labor and it replaces human labor with a machine. Now, the idea is the machine never needs a day off, never needs a vacation, so on and so forth, doesn't have personal problems, and so on. The robot, if it's taking data, will probably take better data. And if you're taking better data and the error's decreased, that'll improve your components of your genetic gain. It's going to increase the amount, it's going to decrease the error, and it's going to translate into better sigma squared G, or sigma, the standard deviation of the phenotypic variance. But primarily, it saves human labor, it improves farming practices or creates new options for farmers, but it doesn't necessarily by itself improve genetic gain. What about UAVs? And let's call it sigma squared UAV. I mean, you can fly drones, you can take satellite imagery, you can look at your crop every day, you can measure a number of variables, you can see changes from certain things, and this is all color-coded for you. But at the end of the day, does it really improve genetic gain? Now, it has great promise to be a real game changer, produce improving genetic gain, if we could predict yield in small plots from aerial imagery or robots or satellites. And I mean, you could just pick the winners without having to pick them all. Okay, and we'll get back to that. But how does color coding based on soil types and yield maps with different colors on them and pulling off this and that in the summertime to show color differences in that. I mean, at the end of the day, it's all real interesting and it's great, and it may help you as a farmer, but how does it help the industry improve genetic gain? The only way it can do it is got to help you measure that phenotype more accurately and then get more of the genetic variance in the end of the game here to improve genetic gain. What about artificial intelligence? I mean, you got kind of sigma squared artificial AI. I mean, you got things like computer vision where the computer can differentiate between different kind of plants and it knows the weeds from the one that wants. And then there's a mechanism to kill the weeds and not the ones you want to keep. What about machine learning? That machine, again, it learns to recognize plants. It learns to count plants. It knows how far apart they're supposed to be. It knows what's the plant you want to keep and what's the plant you don't. And so you can train your robot or your UAV or a whole device all by itself to do these things. You can use all of these things to create new algorithms. Well, what's an algorithm? I mean, it's just a prediction of an unknown outcome from outcomes that you think you know. And you just start down the road to trying to predict based on what you know and things that you don't know, and you fine tune it and you do these things. But at the end of the day, just sitting here and talking about this genetic gain equation, again, are all of these new technologies right now, at this moment, increasing genetic gain in anybody's program? I'd really like to know if they did, if they could show it. And the other thing is, scientists know this and everybody else forgets about it and nobody knows it, is that every time you take a measurement, there's an error associated with the measurement. So if we start bringing more ways to measure in, we're also going to have an error associated of some size, hopefully as small as possible, with every one of those methods. And at the end of the day, they've got to contribute more to getting us to our genetic gain. Because hey, folks, if you're not increasing genetic gain in your program, and you were hired to do that, not everybody is. I mean, if you're running population improvement, if you're doing genetic diversity, if you're bringing in new germplasm, you're not, I mean, you're contributing, but you're not the guy doing it. But the person commercializing products, whether it be brassica, alfalfa, grain sorghum, maize, soybeans, beans, cassava, I mean, any cocoa, anything you can think of, you're supposed to be getting more of it for less. And that's your job. And to me, if you're not doing your job, maybe you ought to quit or get fired. I mean, I hate to say it that way, but it's the way it is. If your job is to write papers from this, okay. But if it's not, if you're in a big company, somewhere along the line, somebody is making these decisions, and the idea is to improve your rate of genetic gain. And they should know what their rate of genetic gain is, and the whole entire program ought to be focused on just how to improve it. That should be the only thing you really think about. That's what you should be doing. I mean, how do you do it? Is it through testing? Is it through genomics? Is it through a new way of looking, whole genome selection? Is it, a new marker system? Is it, having your plants on a conveyor belt and collecting reams and reams of data on phenotypic traits that those cameras and those you can do, and then how to use it, and how to make it work, and how to have an increased genetic gain for you. So I challenge all you fellas working out there to do that. So I'm just going to close. There are things, new technologies promise to be game changers. If you can do yield predictions, accurate. No, I'm not going to say accurate. Yeah, I am going to say accurate. Accurate yield predictions, not necessarily precise, because there is a difference. Accurate yield predictions by swarm bots in the field or by aerial imagery, whether it's satellite or UAV or some other technology. If you could get that down to where you could actually measure those phenotypes, and then you have your robots go out and pick 10% of them or 7%, and then somebody just goes in and gleans the whole field off and you're done. I mean, just think what that would save, huh? besides the money. Unbelievable, the savings. If you just harvested 7% of your plots instead of 100 up, huh? You don't think that would save you some money? If you could increase genetic gain, for God's sakes, why wouldn't you do it? And then the robots operate remotely and independently, and they can do a lot of stuff, be programmed to do about anything. And that's going to be game changers, but it also, if it's just getting people, the breeders and the associates, to sit in the office and watch the robots work, then we got to be careful that we don't become into that, because I believe that there still needs to be that Barbara McClintock feel for the organism that only you can get by walking in the field and looking at your genotypes. You don't have to do it every day. I mean, my biggest thing is I want to be there the days plots are harvested. I want to be there right then. That's when I want to be there. That's how I form my opinion of what these phenotypes are when they end up on a spreadsheet later. So these are things that robots can do, and they can increase precision on phenotypic and genotypic measurements. And if they can do that, robots, aerial imagery, artificial, intelligence, and then they can tie into this genetic gain equation, and they probably should just be on the end of it maybe, or incorporated into it, or knowledge that they're incorporated into it. So today, I'll just leave it that way, and just remember, when you're thinking in the simplest terms, when you're running your breeding program, R sub T, which is the response, is equal to the selection intensity, which you can't change a lot, times the accuracy of selection, which is the one you have to change to get a better sigma squared A, and then years if you can cut time. But you may not be able to do that very much. So I'm almost saying, the years and the selection intensity's out of here. And it's all about accuracy of selection and getting the most additive genetic variance, which is the raw material for selection. So that's what new technologies need to do, not just create air and create assistantships and postdocs. They need to increase the rate of genetic gain, and if they're not, then we don't need them. And I say we do need them. We just need to learn how to make it work, how to make your program work, how to make your program more successful. Because heck, that's what's fun, winning, right? So today, this is David Benson with Cornhusker Hybrids in Lincoln, Nebraska, saying and reminding you that success starts with the seed, and conduct your program to retain the superior genotypes for continued evaluation selection. That's the number one thing you have to do. New technologies are coming in. They need to be improving the rate of genetic gain, not just adding error and uncertainty. So have a great day. I'll see you next week.